Okay, we are live now. Perfect. So, good evening, everybody. It's a great pleasure for me to introduce today's talk because the speaker today is one of the founding members of the PRIMO group. I'm talking about Alessandro Buccini from the University of Cagliari. Alessandro was awarded his PhD at the University of Insubria a few years ago. Then he moved to the US where he worked with Professor Lothar Reichel for a couple of years of postdoc, and then he came back to Italy, and now he's an RTD-A, so a temporary researcher at the University of Cagliari, where he's enjoying sun, beach, but not today because it's a bit cloudy apparently. And today we'll talk about structure preserving preconditioners for L1 regularization. I think you can take the stage, and I hope everyone will enjoy your talk.
Thank you, Marco. Thank you, everybody, for coming to this talk. So, as Marco said, this is a talk by previous academic father, so Marco Natelli, which was my PhD advisor way back when, and Davide Bianchi, which is my academic brother. We share the same. The talk of today will first give some introduction. I mean, I guess that knowing the audience, I don't really need to tell you what discrete closed inverse problems are, so it would be very just to bring everyone to the same page. Then I will talk about iterative regularization method, again, just to fix notation mostly. And then again, image deblurring, because this is going to be my main focus, let's say. Then I will talk about these structure preserving preconditioners, and now actually we construct this precondition and then we apply them to two L1 regularization methods, which are ISTA and generalized brackets. And of course, as customary, conclusion and future. So again, the problems that I am interested here now are linearly closed inverse problems. So we have a matrix. We want to solve, let's say, a least square problem. A is a severely conditioned matrix, meaning that the singular values of A decrease really fast and they converge to zero, and there is no gap, so we cannot determine a numerical value. We have measure some data B delta, where the delta up here signals that there is some noise in the data, so it's not actually accurate. We have some measurement error, discretization error. And then we have our unknown X, which is the signal, and for the most of the talk, it's going to be an image that we want to recall. So as we said, A is enclosed, so is ill-conditioned, sorry. So if we simply solve the least square problem by applying a dagger, the Moore-Perot's pseudo inverse of A, to B delta, we get something that usually is completely useless as it is corrupted completely by noise. We would like to find a sort of approximation of this X dagger, which is a dagger B you see here without the delta, so the noise-free right-hand side, which we, of course, don't. To do that, a possible approach is regularization methods, which basically substitute this ill-posed problem with the well-posed nearby. And the solution of the well-posed one is hopefully a good approximation for X delta. Well, of course, one of the most famous and easiest one is Tikhonov regularization, because it's kind of a strange word, but it's of course one of the most popular. And so we add to our least square term, so our data fitting term, a regularization term in the two norm. So this problem here is basically telling me find X so that AX is close to B delta, so that your reconstruction X mu depends, it's close to fits the data that we should see, but at the same time such that the norm of LX is small enough. If we pick L equal to the identity, we talk about standard form. Econo is said to be in standard form, and simply means please find something that is a small 2 norm, which means doesn't oscillate too much. Otherwise, if we pick L to be something different than from the identity, then we are talking about econo in general form. And in this case, it's find something such that, find an x such that Lx is of small norm. Like, for example, if L is a derivative, then we say something, find something that is smooth enough, it doesn't oscillate. So we assume the null space of A and the null space of L intersect trivially, so the solution of this minimization problem is unique, and you can find it by solving this linear system of equation with matrix A transpose A plus mu L transpose L, which is symmetric, well-posed if you choose L in a clever way, and symmetric and positive definite. This is not, of course, the only approach that you have that we can use to regularize or find a regularized solution. The one that we're actually interested in here now is iterative regularization. So the idea is that you start from a certain approximation of your X dagger, might be the zero vector if you don't have any information, or might be something else, and then you start iteratively to refine your solution to get a better and better approximation. So what is the easiest one that you can think of is gradient descent. So we want to minimize the functional J of X, find the minimizer of the functional J of X, and let's say that J of X is differentiable and complex. We like and strictly complex, let's say something that it's easy to deal with. So we have an approximation xk of this minimizer, and we know that the direction of the steepest descent on k is minus the gradient of my function of j, and so we can obtain an improved approximation xk plus 1 by simply taking a step into the steepest descent direction. And the step length is this mu here, omega here, this parameter that is appropriately chosen so that this iteration actually converges to a minimizer of this rate. So if in our case we get our J, which is our 2 norm of the residual, well, this is just convex if the null space of A is non-trivial. Okay. So the gradient or minus the gradient is just A transpose times the residual B delta minus AXK. And so when we compute our gradient descent iteration, what we get is the so-called Landweber iteration. Right? So we have our xk plus 1 is xk plus parameter times A transpose the residual. This is basically Richardson method applied to normal equation related to the least square problem. So it's possible to show that if we pick our mu between 0 and 2 over sigma 1, which is the largest singular value of A squared, then this guy here will converge to the minimizer of the solution of the least square problem that is closest to x, which means that if x0 is equal to 0, then it's the minimum norm solution. Now, this is not actually a good news because this is A dagger B if we pick x0 to be equal to 0, and this is not something that we like. So how can we actually get a decent reconstruction? We said that we don't like that. Well, we can obtain that by early stopping the iteration. So instead of doing the infinite amount of iteration that require a large number, we stop soon enough. So here the idea, it's very simple. This is, let's say, these are a stop, the train, and you start from home city, let's say, and you want to go somewhere. Now, the point is like your train here is going to the front seat, not the one that you wish to visit. But at some point, but it's going right, kind of in the right direction. So the first iteration, the first stops are getting closer and closer to the city you want to visit. But at some point, you will go away from your desired city. So you want to stop when you are close enough. This is the more mathematical term is behavior. It's referred to semi-complete. So it means construction error, X dagger K, is decreasing throughout the first iteration, and then you reach an optimal iteration, and then you start to increase. So you are getting closer and closer and closer to X dagger, but at some point the noise will start and the if condition will start to play against you, and you will go away far from the desired. You can stop, of course, in many ways. For us, the most relevant one for our tool right now is the discrepancy. So you want to stop as soon as your residual is the norm of AXK minus B delta is decreasing, and eventually it will reach its minimum. And eventually it will be smaller than tau delta, where delta is an upper bound for the noise. So yeah, correct. So it's an estimate of the. So the idea is like you are basically getting closer and closer and closer. Dagger, to the least square solution, the one that you don't like, and you stop as soon as the residual is smaller than this. Why it is an interesting stopping criterion for us? Because let's call X delta the solution that you obtain stopping, let's say, the Landweber iteration at noise level delta, that what it holds is that as delta decreases to 0, X delta converges to the exact. This is good news. Basically telling you if you don't have a lot of noise, you can expect decent reconstruction of your desired solution. Now, this is in general the definition of an iterative regularization method, which is an iterative regularization method supplied the stopping criterion such that these conditions is satisfied. Landweber is not, of course, the only iterative regularization method. GEMRES and CGLS are other examples, but for us, Landweber in this case is of particular interest. So this is the end of the story. Now, of course not. I still have 29 slides, so I probably still have something else to say. So it happens that Landweber is very slow and not that accurate at the end of the day. So we want to, first things first, speed up the convergence. I don't want 8,000 iteration. I don't have patience. And if in the process we can improve the accuracy, well, we wouldn't complain too much. So let's open our linear algebra book or numerical linear algebra book, and let's see what it's usually done for well-posed linear system to improve the speed of convergence. Well, it's preconditions. It's among the techniques. So what's the idea behind the preconditions? So let's say that A is square, invertible, and well-conditioned. Wonderful word. And let's pick a matrix P such that P to the minus 1 is a decent approximation of A to the minus 1. And matrix vector product with P to the minus 1 are easily computed, right? So usually matrix vector product with A to the minus 1, so inverting A, it's difficult. We are having a computer approximation of A that is easily inverted. We multiply on the left by this P to the minus 1, and now what happens is that P to the minus 1 A is a good approximation of A. This is not too far from the identity, so we basically solved the linear system, right? So this is a much easier system to solve because P to the minus 1A is similar to the identity. This is the intuition. What actually happens in practice is, for example, Krylov methods. What they do is that they invert one eigenvalues of your matrix at each iteration, intuitively, kind of. And if you want basically P to the minus 1 to cluster the eigenvalues of A so that you have just few distinct eigenvalues, iterative method will converge in a few steps. Ideally, if P to the minus 1A has only 2 distinct eigenvalues, then the Krylov method should converge in kind of 2 iterations. This is the intuition. I'm not very precise here. I know it's just to give an intuition of what should be going on. Perfect. So we are done again? No, Why? Because, well, first things first, we don't have any vertical A. Here's, let's substitute here a -1 with a dagger and we're done. No, again, because a to the minus a dagger is extremely close, and its norm is huge, right? It's 1 over the smallest singular value a, which, as we said, converges to 0. So it's a huge value, difficult to treat. And also, we don't want really to compute a dagger a times x because, sorry, a dagger b. We don't want to compute that because, as we said, we hate that thing. It's the one that is corrupt. So we need to find an approximation of the inverse of a that is regularized. So constructing precondition for ill-posed systems, it's not that trivial. It has to be done very carefully. You want to speed up, but not too much. And you don't want to be too close to the inverse because the inverse will do so. Again, intuitively, why you don't want to speed up too much? Again, think about the idea before of the train. If the train does a lot of stops, then yeah, it will take you a lot of time, but hopefully we'll get pretty close to the city that you want to visit, even though you're not passing through that. But if it does just a couple of stops, if you miss your stop, you will be completely screwed up and end up in a city that you didn't care. So let's construct the precondition finally. Okay, let's think again about this preconstruction EK. So solution that I desire minus current approximation. If I have an approximation of my k, let's say hk, then xk plus hk is an approximation of xk plus ek, which is actually my desired solution. So my improved xk plus 1, I can write it as xk plus this correction. So I need to find a good approximation of my approximation. Now, again, if we set hk to be omega times a transpose residual, we get Lund value. But this is not what we want to do now because we get back again to Lund value, back to square 1. So let's call k the residual. So this is b delta minus axk. So who is xk? X dagger minus the error. So this is b delta minus ax dagger is my true noise-free data that I don't have, plus aek. So this is the noise, right? Plus aek. So ek can be found by solving this linear system of equations, right? This is exactly the same as we saw before. This is another ill-posed problem. The right-hand side is affected by some noise unknown, and my desired solution now is no longer the clear image or whatever signal I'm interested in, but is the reconstruction. And this is the so-called error equation. Well, we already saw how to solve these guys here. Let's use Tikhonov in standard form. So we can find an approximation EK by solving Tikhonov and HK by solving our Tikhonov minimization. Again, this means that I put L equal to the identity, so we obtain our HK, it's just A transpose A plus mu I the identity, sorry, the minus 1 A transpose R. And we get this iteration, right? And this is what we call iterated Tikhonov. Now, no one forces me to pick the same mu at each iteration, so I have a mu k here. No one tells me how to choose this mu. Well, actually, someone does. Anke and Grotesh in 1998 told us how to choose this mu k, so that, again, this is an iterative regularization. If we choose mu k so that this condition holds, which simply means if mu k shouldn't increase too much. If it decreases or it's constant, it's perfect. But if it is increasing the sequence, it shouldn't be increasing. And if this condition is satisfied, then, and we start from 0, then the iteration converges to the solution of mu. And how we obtain regularization? By early stopping. So, but we can see this iteration as flexible. I put it flexible because I can change the technical preconditioned version of the Lund value. So let's call P this 1 over sigma 1, this is just a constant in pairs, square root of A transpose plus mu the identity. Now let's have a look at this. Well, if let's say if A were symmetric and positive definite, symmetric and positive definite and everything, and mu is equal to 0, then this is just again A, but this is not the case. So we have a regularized version, right? You have this plus mu the identity that shifts the singular values up. And let's consider the system is the minus 1A is equal to the P minus delta. Let's pick omega to be sigma squared, and let's apply Landweber. And lo and behold, a little bit of linear algebra, and you get the iterated T. So iterated T cannot is just Landweber left preconditioned to this matrix here. Okay, so this gives us an idea, like this precondition, right? So we have found a good precondition for Landweber. Okay, so let's concentrate for a second on imaginative learning, right? So let's see how we can actually construct these preconditions. So let's think about imaginative. So I'm pretty sure everyone is a little bit familiar with this, so we go fast. This is the continuous problem. It's a three-domain integral function of the kind. So you have your desired image F, and we assume the blur to be same everywhere. So it's, you have your integral curve K that doesn't depend on the location, so it's just a convolution here. And this is the once discretized for the SF. So you have your blurred image G. It's just a weighted average of the entries or the point of the values of your image F with weights determined by these two. And you discretize this thing here with some connotation method, let's say, and you get a matrix A, which is very condition. Obviously, this integral here is over R2, which is not fun. When we discretize, of course, we only look at a small window, which is called the field of view. It's what your camera can record. It cannot record the whole universe, just can record a small window. But what's inside my box, my field of view, depends also on what is outside, right? This is, again, it's a weighted average, and the weights, if you're close enough to the border, will, let's say, go out, right? So the blurred point inside your field of view depends on what is outside. So what you're dealing with is an underdetermined system. You have the data inside the field of view, but you need the data inside your field of view and some data outside the field of view. Of course, one can say, oh, well, I can deal with an underdetermined system. You can say, well, let's impose some boundary conditions. I'm going to make assumption of what is outside my field of view. I can say, oh, well, everything is zero, everything is black. This is pretty good with astronomical imaging. Or the image is like reflected, like mirrors, or it's anti-reflective, or it's copied and pasted periodically. And we call the PSF basically the discretized version of K. So you apply your matrix A to a vector that is just as one, the delta, right? It's one in a point else, which again, if you go back here, this is the equivalent of putting here a Kronecker delta, and you get that. Okay, but this PSF, it's an image, right? We represent it as a vector, but you can think of it as an image. Well, it's an n by n image. I'm going to take everything n. I'm going to be, so the image is square, and it's the product of two odd numbers. So let H be my PSF, we shape. Now it's an image. It's basically a blob. Right? And let's index the pixel where the center of the PSF, or where the delta was. Be indexed in 0, 0, and then we can write down function phi, which is just a trigonometric function whose coefficients are given by the entries of the pixel. And this is called the symbol, right? So the entries of the PSF are just the weights, let's say, of my, or the coefficient into my trigonometric polynomial. Why this function phi is interesting? Because this symbol gives the spectral behavior of A, and this is the fun part, independent of which boundary condition I impose. What will happen is that the eigenvalues of A, if n is large enough, are a sampling or well approximated by a sampling of this uniform sampling, uniform grid of this function phi. And you will have few outliers whose number will go to 0 compared with that. They are small over. So when we impose zero boundary condition or Dirichlet boundary condition, which means take everything that is outside the image and put it to 0, you obtain a matrix that is a block triplet with a block matrix. If you assume that the matrix is circulant, you assume periodic boundary condition, which means that the image is copied and pasted on the left and right of the bottom below, you have that in matrix A, it's a block circulant block. And we denote the matrix A, the triplet one, Tn of phi, but the most important one, the circulant one, Cn of phi. Okay. So what happens is that if we use periodic condition, then my matrix my matrix A is actually diagonalized by the Fourier transform, right? The DFT matrix, and the eigenvalues are exactly the sampling of that function phi, that symbol phi that we talked about. Okay, so I know exactly the eigenvectors are the Fourier vectors, and I know exactly the eigenvalues, which are just a sampling of this symbol phi. If we impose different boundary conditions, then my matrix A will have some structure that will be denoted by n phi, and we will always be able to write it as Cn plus a matrix of small and plus a matrix of small. And in any case, these phi here are actually a good approximation of the, these numbers here are a good approximation of the eigenvalues of a matrix A. Okay, finally we get to our stationary, structure preserving. So let's consider this iteration here. We have xk plus matrix zk times the reciprocal. Now, if we pick zk to be A transpose, we actually get our Landweber method. And if you pick zk to be A transpose plus mu k to the identity, we have the iterated. So recently, Donatelli and Hanke said that, proposed the idea of saying, well, yeah, this means that at each iteration I have to solve a linear system with A transpose plus mu k the identity. This is not fun. K is large and the structure is not that easy. Maybe this is kind of a pain to solve this system. But since my circulant one is pretty close to A, why don't I simply use the circulant? So instead of saying, well, let's use the exact structure that I want, let's just pick circulant with the same symbol. And so zk, it's again a circulant matrix because the circulant matrices are forms in algebra. So, and the symbol is a regularized version of 1/5. So the symbol of this matrix here, it's just phi conjugate of phi over absolute value of phi squared plus mu k. Now, if you pick mu equal to 0, this is exactly 1/5. And you get back the inverse of C phi. But why do we want to discard? Why discard the structure? Maybe it's useful. I mean, that structure incorporates a lot of knowledge of our image. I mean, the structure is chosen on how the image looks like. I mean, if you have, again, an astronomical image, 0 means something. If you have a real image, think about like scenery, if you copy and paste above and below, it would mean that you have, I don't know, some grass and then the sky. If you copy and paste it, you will have above the sky some grass and below the grass sky. Doesn't make any sense, right? So what they did in this paper was, well, let's pick same symbol of my matrix ZK, but the structure that I need, so structure that makes sense with my image. And this is motivated by the fact that, well, basically, it's true that for any of these kind of structure, the product of the matrix with symbol G and F is a matrix with symbol G times F. Is this true? Well, no, but it's a good approximation. The last thing is how we choose mu-k. Well, mu-k is crucial because if we pick a wrong mu-k, we are stupid, let's say, and we pick mu-k equal to 0, we'll destroy everything. If we pick mu-k to be 10 to the 10,000, we're not going to see anything. So in the original paper, they propose a way to choose it, which is actually solving these linear equation, this non-linear equation. Now, I don't want to get into the details, just means that these equation here allows us to prove some theory. The idea here is that if we have if Cn and A are close enough, then what we will have is that if we pick Zk to be actually the circulant, the iteration will converge monotonically, meaning that the error will decrease monotonically, and it is a iterative regularization. Now, if Zk has the same structure of A, well, the proof of convergence is not available yet, maybe never, who knows, but the results are pretty good. Okay, so we saw how to construct this preconditioner. Let's plug them into some L1 regularization. So let's go back to Tikhonov. And of course, we can generalize easily by, instead of having here a 2, we can put a q, any q greater than 0, right? We don't want an NPR. If we have q smaller than or equal to 1, this is the when interesting stuff happens, because we are imposing sparsity. We all know that. And if L is the discretization of the gradient, we have the total variation. If L is that can be the Fourier transform, a wavelet transformation, whatever you like. For us, we will be Q equal to 1 and L equal to W, a wavelet transform, a framelet transformation. In other words, a rectangular matrix such that W transpose W is the identity. So let's consider our W here. W transpose W is the identity, so I can plug it between here. I can call AW transpose K, I can call WXY, and I have a new linear system, KY equal to B delta. I can simply solve this guy here, get Y, and then my X is just W transpose. So we can ignore this W here and just solve this problem here, this regression problem here, where we have AW transpose X minus B delta norm 1 of X. We want this wavelet or framelet coefficient to be sparse, and then once we have this solution here, I multiply with W transpose and I get my image. So how do we solve this problem here? Well, this is probably one of the most famous papers out there about this. We can use ISTA, iterative soft thresholding. So this is our iterative soft thresholding in iteration. So we have one step is a forward vector optimization method. So you have one step of gradient descent, and then you have your soft thresholding. But wait a second. This is just Landweber again. This is our old and beloved Landweber iteration. So this means that I know how to precondition this system. And it's natural just to change this iteration here to this, the zk in front of here, and put some precondition instead of just a transpose. So first, Wang and collaborators here, they propose to use the circulant matrix, right? Nice. And how do we pick these parameter here? Well, again, let's use that non-linear method here, just because then the theory turns out nice. We are interested in using, instead of Tikhonov in standard form, instead of having here the identity, to have Tikhonov in general. So first things first, here we have our operation here. So simply put, instead of the identity, L transpose or L transpose L, if you put the C transpose on the other side, it doesn't change it. And we have our PISTA algorithm, precondition, the iterative software shielding algorithm. So where we have preconditioner in front of the Landweber iteration. If we assume some stuff, let's say, which is not really important, and for example, we pick L to be this function here, again, not very important. And if we select alpha, as I said before, with the non-linear equation, then we can show that PISTA is an iterative regularization method and that the reconstruction error decreases monotonically, stopping with the discrepancy, which is nice. Obviously, we can do the same game. So let me go back a second. I know it's not up. Why choosing the circulant structure, which is not very fun, and it's not the most accurate one? Let's pick the structure that I'm actually interested in. So we construct this guy here, and we have the structured version of PISTA. Sadly, we gain a structure, we lose a proof. So we cannot show that this guy here actually converges, but numerically, it works pretty well. So let's give an example, which is always fun. We have an image. This is my PSF. This is basically handshaking blur. So I was taking a picture of this man taking a picture, and my hands were shaking. We add 2% Gaussian noise, and since the image here is generic, we impose reflexive boundary. Image is reflective, left and right, like mirrors, like if I put mirrors here, here. And this is a result, our plain ISTA, our preconditioned version. So we lose something in RRE actually, but gain something in similarity index. This is a number that tells you how much your eyes perceive the true image and the computed image similar. And the structured version, you see it actually improved a lot. What it's really interesting to look at is that both method ISTA and the preconditioned one have some strange thing happening. Boundaries here, some boundary effect that we don't like, some bridges like that. The structured version completely kills those oscillations. So using these structure actually has some nice effect. And this is seen exactly in these like good increase of the SSI index. The other, I don't have a lot of time, I'm really out of time, so we'll really fast here. Let's consider these other kind of problem. This was used mostly by Kayosh and Shen for compressive sensing, but it's being used also for image deblurring. Mostly, this is again, you have to stop with discrepancy. And to solve this problem here, sorry, we use the linearized Bregman split. Again, we have these iterations. These are basically the ISTA one. The only difference is that in ISTA here you have here you have, sorry, a ZK. Here you have an XK. That's the only real difference of these two things between the two algorithms. But it actually makes a lot of. What really matters is that here we already see again our loved and beloved Landweber. So let's precondition it. Again, in this paper, Kai, Donatelli, Bianca, and Monk, what they did was precondition with a second precondition. And they call this non-stationary modified linearized Bregman. And again, you stop the iteration with the discrepancy principle, and you obtain an iterative regularization method whose reconstruction error decreases 1/2. What we did in this paper here was, well, let's introduce the structure, same game as before, and we called our method structure non-stationary modified linearized Bregman algorithm. Yeah, here B and L should be clear. Sorry about that. Again, another example, and you immediately see again there's pretty large improve in the quality of structure and of the similarity. So let's conclude. What we have done is we introduce some preconditioners and we describe how they were constructed. They don't need the estimation of any parameter or only a few. And we have proved their effectiveness with some numerical examples. So what can we do? Well, there are still a couple of parameters to determine, so it would be nice to also have those completely covered and have like full plug and play method that anyone can use just by pushing a big colored button. And we need some theory about the structure. And the other thing is like, well, it would be nice also to work with nonlinear problems, and with some colleagues here, University of Cagliari, and some colleagues now at GSSI, we started to work something on geophysics, so maybe we could apply stuff here. Geophysics. I was late, sorry about that, and thank you for your attention.
Thank you, Alessandro. I don't know if you can see me. Yeah. Actually, you were not too much late, don't worry. It was 40 minutes more or less. I was going to stop you, but then I realized you were going to finish, so I stopped. So thanks a lot for this interesting talk. Let's see if anyone in the audience has a question for you. Let's wait a bit. If you can unmute yourself, or you can write it in the chat if you have one.
Or I bored everyone to death.
Yeah, no. So maybe I have a couple of curiosities I have about this, because I followed your talk with the eye of an optimizer.
Mm-hmm.
So when I see that you pre-multiply your gradient by something which is ATA plus something, that is Levenberg-Marquardt.
Yes.
In my point of view of things. So and so again, when you do, it looks like more than from an optimizer point of view, I would more see it as a second order method, let's say, than a preconditioned version, but it's a matter of terminology maybe.
Yes.
And are you planning to do something different from the standard ISTA iteration? So try to see because if you can apply some ideas to more efficient, let's say, algorithm with respect to the naive gradient method and the ISTA method, because I see that these are second order methods, and of course they could be very useful for you. And can you move your ideas about structured preconditioners to actual second order methods, something like that?
Okay, so let's start by saying that I'm very ignorant about optimizations, so I'll probably say something really, really stupid here.
No.
I hope you forgive me. So the idea here is that intuitively here, yes, you're right. And I have to say also in this paper here, this is basically Levenberg-Marquardt method. This new K here is chosen using the interior point Levenberg-Marquardt technique, translated into the into this framework, or as you said, like language.
Yeah.
So the idea, yes, what can be done here, why did they switch to imaginative learning is that as long as your matrix A here, which is, or your A transpose, so your action matrix, has some sort of structure here. So the idea is like, yes, you can apply this kind of technique to any time you have basically an action matrix with a given structure. So you have, for example, let's say that your action is block Tetris with block, or your A is block Tetris with Tetris block. This matrix, this system here is not very difficult, but it can be difficult or time consuming to solve. So whenever you can take this matrix here and has some structure, you can and you can write it, let's say, go back here, please. Whenever you can write your A or your action as a circulant matrix plus a small correction, then this can be done. So as soon as your matrix A has this kind of structure, actually can be done even better than this. You can also have a diagonal matrix in front of here and it's still okay. So as long as you have that your action matrix can be written as the product, in this case, of diagonal matrix times a circulant plus something small, you can play this game. It's kind of, and the moment that you say, well, A doesn't have any particular structure, it's just, I don't know, a sparse matrix, then things start to get more complicated. It's not a structure that this kind of method can handle. You kind of need to have circulant or tuplets plus correction. Eventually, a diagonal matrix that multiplies as 7. Kind of the best you can do.
Yeah, I see.
Probably for nonlinear function, this is kind of tough to make it come out like this. Maybe I don't know. I mean, but yeah, you need sort of structure to be able to exploit it. Otherwise, you're guy.
Yes. Okay. Okay. Let's see if there are comments or remarks from the audience. Well, looks like not. So maybe we can also stop here for today. I just wanted to thank you again and thank all the people who came to attend this seminar today. And I want to just inform all the audience that next talk in the PRIMO talk series will be next week. So we will anticipate the next talk, since in a couple of weeks there will be CMLA 21, which it's probably going to involve a lot of people in the audience, or at least in the potential audience of the talks. So we are anticipating the next talk to next week. So, and then we will meet the week after the CMLA conference. So that's all for today, and thanks a lot again.